जी बेटा, अस्सलाम वालेकुम. All right, so today we are going to solve paper 3, and this question is related to enthalpy changes, right? This is May-June 2018, paper 32, question number 2. All right, so this is question number 2, and this is related to enthalpy changes. All right, so let's read the question first. Now it says that in this experiment you will determine the enthalpy change delta HR for the decomposition of calcium hydroxide to calcium oxide, right? So we are heating calcium hydroxide and it decomposes into calcium oxide, and we have to calculate the delta HR for this reaction. So on heating, calcium hydroxide decomposes into calcium oxide and we have to calculate delta HR. To do this, you will determine the enthalpy changes for the reaction of calcium hydroxide and calcium oxide with hydrochloric acid. So we cannot measure the delta HR for this reaction directly, and the reason is we are heating solid. So for solids, when we heat solid, we cannot measure the heat energy absorbed. So we cannot measure the temperature changes when we are heating solid. So we have to take the alternate route. We have to calculate the delta HR through Hess's law, which says that energy change does not depend upon route. So to calculate the delta HR for this reaction, what we are doing, we are reacting calcium hydroxide and calcium oxide with hydrochloric acid. So alternative reactions are calcium hydroxide reacts with hydrochloric acid. We are going to measure the delta HR for this reaction. And calcium oxide reacts with hydrochloric acid. This we are going again to calculate the delta HR. And it is easier to calculate the delta HR for these two reactions because these reactions are happening in solution. So we can measure the temperature changes in solution by putting the thermometer in the solution. All right. Now you will then use Hess's law, which says that energy change does not depend upon route, to calculate the enthalpy change for the reaction above. Now what we have Fb2, which is a 3 mole per dm cube hydrochloric acid, Fb3, which is calcium hydroxide, it would be in solid form, and Fb4, which is calcium oxide, again it would be in solid form. So first we are going to do the experiment of calcium hydroxide with hydrochloric acid, and the other experiment would be calcium oxide with hydrochloric acid. Determination of the enthalpy change for the reaction of calcium hydroxide Fb3 with hydrochloric acid Fb2. Okay, let's read the method. Support a plastic cup in the 250 cm3 beaker. So let's suppose we have a plastic cup. Let's say this is our plastic cup. Right, we are going to support it in a 250 cm3 beaker, just to provide it a support. Right, so this is beaker, this is plastic cup. All right, now weigh the container with Fb3, record the mass. So you would have two containers, one would contain Fb3 and the other one would be containing Fb4, and both would be labeled. So because right now we are doing the experiment with calcium hydroxide, which is Fb3. So first you would measure the mass of container with Fb3. So let's suppose this is our container which contain Fb3 in solid form. So we are going to put it on the weighing balance and record the mass. So the first mass would be mass of container with Fb3. Container plus Fb3. And the mass that I got was 43.0 grams. All right, so this is the mass of container plus Fb3. Then the next part is use the measuring cylinder to transfer 30 cm3 of Fb2 into the 100 cm3 beaker. Now what next you would do, you would take a measuring cylinder. Let's suppose this is our measuring cylinder. Okay, and this is, let's suppose it is a 50 cm cube measuring cylinder. We are going to use 50 cm cube measuring cylinder, and you're going to transfer 30 cm cube of FB2. So let's suppose this is 30 cm cube FB2, which is hydrochloric acid, into the 100 cm cube beaker. So first you take 30 cm cube of FB2, 30 cm cube of FB2, and then we'll transfer it into a 100 cm cube beaker. All right, so this is our 100 cm cube beaker, and we transfer all this 30 cm cube FB3 into the beaker. All right, next what we have to do, place the beaker on the tripod and gauze and heat FB2 gently until its temperature is between 35 degree and 40 degree centigrade. So what next you would do, you would place this beaker on a tripod with a gauze on it, and we're going to heat, and we'll place a thermometer in the beaker to record the temperature. So let's suppose this is our thermometer, and we have to heat it up to the temperature until temperature rises between 35 and 40 degrees centigrade. Right, turn off the Bunsen burner. Once the temperature is between 35 and 40 degrees centigrade, turn off the burner and carefully transfer all FB2 from the 100 cm cube beaker into the plastic cup. So you'll transfer this solution of FB2 into this polystyrene cup, this plastic cup. Right. Carefully transfer all FB2 from the 100 cm cube beaker, this is FB2, into the plastic cup. So you transfer it into the plastic cup. All right, next, measure and record the temperature of FB2 in the plastic cup in the space below. All right, measure and record the temperature of FB2 in the plastic cup and space below. So you'll place a thermometer in the plastic cup, and we had 30 cm cube of FB3 in the plastic cup. This is FB2. Right, and you'll note the initial temperature, and the temperature that I got is 40 degrees centigrade. So initial temperature. So initial temperature, or let's just write the temperature readings separately. So let's say initial temperature, once we added 30 cm cube of FB2 into the plastic cup, the temperature which we get is 40.0 degree centigrade. Right. Then immediately add all the FB3 from the container. This FB3 which we had in the container, the mass we have already taken it. Immediately add all the FB3 from the container to the FB2 in the plastic cup. So we'll add this FB3 into the plastic cup. Right. So once we've added this into the plastic cup, then reaction will start. Stir continuously until the maximum temperature is reached. So it is an exothermic reaction, temperature will rise, and you have to note the maximum temperature. So the final temperature which we get, or maximum temperature, is 62.0 degree centigrade. So this is the final temperature. Right, measure and record the maximum temperature, and weigh and record the mass of the container with any residual solid. Now, weigh and record the mass of the solid with any residual solid. Once you have added this FB3 into the plastic cup and you have noted the temperature, now you'll take the mass of this empty container just to know that what amount of FB3 we have added in the plastic cup. So the mass of container which we got is mass of container plus residual solid is 41 grams. Right, so from here we can calculate the mass of FB3 that we have used. We have the mass of container plus FB3. Initially it was 43 grams, and then we have added FB3, then mass of container plus residual solid is 41 grams. So the mass of FB3 used mass of FB3 used is 2.0 grams. Right, this is the mass of FB3 used. And now let's calculate the change in temperature, because we have the final and initial temperature. So the change in temperature, that would be equal to 62.0 degree minus 40.0 degree. So this is 22.0 degree centigrade. Right, so we have all the 6 readings that we need. Now we have mass of FB3 used. That means when we have added 2 grams of, what is FB3? FB3 is calcium hydroxide. So when we have added 2 grams of calcium hydroxide, the change in temperature is 22 degrees centigrade. Right, so this is an exothermic reaction. Now the next part is related to calculations. Next they are saying calculate the energy produced during this reaction. What amount of energy is released? So whenever we need to calculate the energy released or energy absorbed, so the formula we are going to use is Q is equals to mc delta T, or because energy is being released, so we can use Q is equals to minus mc delta T. Now this formula Q is energy released or energy absorbed, right? In this case it is energy released. M is the mass of the solution of which we have noted the temperature. C is specific heat capacity, and they have given us the, assume that 4.2 joules of heat energy changes the temperature of 1 cm cube of the solution by 1 degree centigrade. So 1 cm cube of solution, to raise the temperature of 1 cm cube of solution by 1 degree centigrade, 4.2 joules of heat energy releases. So this is the specific heat capacity. Okay, which is represented by C, and they have given us the value 4.2. So we have to calculate Q. Now the mass of solution, what mass of solution we have to take? Now you have to understand this thing, that you have added 30 cm cube of FB2 into this container, in this plastic cup, and then you have added calcium hydroxide. Now the thermometer was placed in the container, you were recording the temperature, right? And the temperature that we have recorded is the temperature of surroundings. And in this case, surrounding is solvent. Just remember this thing, that we are measuring the temperature of surrounding, and in this case, the surrounding is solvent. So we are measuring the temperature of solvent, which is in this case water. So we are measuring the temperature of water. So here we will make an assumption that we have pure water, although it is a dilute solution of acid, but just to solve this question, you would assume that this is pure water, and we have 30 cm cube of water. In all the calculations of enthalpy changes, you have to make this assumption that you have pure water. And for water, we know this thing, that the density of water is 1 gram per cm cube. That means for water, 1 cm cube is equals to 1 gram. So if we have 30 cm cubes of water, that means we have 30 grams of water. So the mass of water that we have is 30 grams, right? The temperature rises, right? The temperature change which you have noticed, this 22 degrees centigrade, this is the temperature change which occurs in water when we have added calcium hydroxide into hydrochloric acid, right? And we are taking the specific heat capacity. This is the specific heat capacity of water. So we have to take the mass of water, and for mass of water you just have to do this thing, just find out what is the volume of solution that we are using and convert it into grams, because for water 1 cm cube is equals to 1 gram, right? So that means we have 30 grams of water multiplied by specific heat capacity is 4.2 into change in temperature is 22. So what would be the final answer that we get here is, so this would be minus 2772 joules of energy would be released, right? So I hope you all get this idea that how we have to take the mass of the solution, right? We just make this assumption that this is pure water, right? And for pure water, 1 gram is equals to 1 cm cube. So if we have 30 cm cube of solution, that means we have 30 grams of water. If we have 40 cm cube of solution, that means we have 40 grams of water. So in all the calculations of enthalpy changes, you have to make this assumption. You have to make this assumption that we are doing the reaction with pure water and we are measuring the temperature of water. So whatever the volume of solution, just convert it into grams. Now the next part of the question is calculate the number of moles of calcium hydroxide Fb3 used in the experiment. Moles of calcium hydroxide. So moles of calcium hydroxide, we have mass of calcium hydroxide. We have used 2 grams of calcium hydroxide. So we have to convert mass into moles. So that would be equal to mole is equals to given mass upon mR. We have used 2 grams divided by calcium hydroxide molar mass CaOH2, calcium 40, oxygen 16 plus 1, 17 into 2. So that would be equal to 34 plus 70, 74. So 2 divided by 74, this is 0.027. 0.027 moles of calcium hydroxide. Now the next part of the question is calculate the enthalpy change in kilojoules per mole for reaction 1 below delta H1. Right, for this reaction, when we have added calcium hydroxide into an aqueous solution of HCl, calculate the delta H, and delta H would always be measured in kilojoules per mole. So that means first we have to convert our joules into kilojoules. So in kilojoules that would be 2772 divided by 1000, that is equals to 2.772 kilojoules. Now we have to calculate per mole. So the amount of energy, this amount of energy is released when we have added 0.027 moles. So we can just simply make a relation here that when 0.027 moles of calcium hydroxide is added, the amount of energy released is minus 2.772 kilojoules. So this is the amount of energy released when 0.027 moles of calcium hydroxide is added. So what if we add 1 mole of calcium hydroxide? So 1 mole of calcium hydroxide, what amount of energy would be released? So just simple maths here, cross multiplication, we get X is equals to minus 2.772 divided by 0.027. So that would be equal to 0.027, and this is 102 minus 102.67 kilojoules per mole. So this is the amount of energy released when 1 mole of calcium hydroxide, 1 mole of calcium hydroxide is added in excess hydrochloric acid. When 1 mole of calcium hydroxide is added in excess hydrochloric acid, the amount of energy released is minus 102.67 kilojoules per mole. Alright, so very simple calculation. Now this is the first part of the question. In the second part, we have to do the same experiment, but this time we are going to take calcium oxide. So the procedure would be almost same. Support the second plastic cup in the 250 cm cube beaker. Again, weigh the container with Fb4, but this time Fb4 is calcium oxide. So the mass of calcium oxide that I get is mass of Fb4 plus container, mass of Fb4 plus container, that is equals to 43.0 grams, and mass of Fb3, mass of residual. I'm just writing all the values because we know what we have to do. This is the same experiment, but we are only repeating it with calcium oxide. So everything is same. So mass of residual plus container, that is 42 grams. So that means this time we are using mass of Fb4 that we use is 1.0 gram. So this is mass of Fb4, and then temperature. So when we added initial temperature, when we added hydrochloric acid 30 cm cube of you can just read this, that use the measuring cylinder to transfer 30 cm cube of Fb2 into the 100 cm cube beaker. Same. Place the beaker on the tripod and gauze and heat gently. Its temperature is approximately 35 degrees centigrade. Carefully transfer all the Fb2 from 100 cm cube into the plastic cup. Right, so measure and record the temperature of Fb2 in the plastic cup in the space below. Immediately add all the Fb4 from the container to the Fb2. So initial temperature, when we added Fb2 into the plastic cup, initial temperature is 34.0 degrees centigrade, and final temperature is 62.5 degrees centigrade. Right, so change in temperature, delta T, that would be equal to 62.5 minus 34. So this is 28.5 degree centigrade. This is the change in temperature. Now calculate the enthalpy change in kilojoules per mole for reaction 2 below delta H2. So for the energy change which occurs when calcium oxide is added into hydrochloric acid, they are calling it delta H2. Previously, when calcium hydroxide was added, that was delta H1, and this is delta H2. So we have to do the same procedure again. First we will calculate Q is equals to minus mc delta T. Again temperature is being released. Mass of water is again 30 into C 4.2. Delta T, this time it is 28.5. So 30 multiply by 4.2 multiply by 28.5. So that is equals to 3591 joules. Alright, next we are going to calculate to convert it into kilojoules. So divided by 1000. So that would become minus 3.591 kilojoules. Next, calculate the moles of calcium oxide that we have used. So moles of calcium oxide would be equals to what mass of calcium oxide we have, 1 gram. 1 divided by the MR of calcium oxide, calcium 40, oxygen 16, that would be equal to 56. So 1 divided by 56, that is equals to 0.0178, 0.0179. Right, these are the moles of calcium oxide. Finally, we are going to calculate the kilojoules per mole. So again, we can make the relation that when we added 0.0179 joules of 1.0179 moles of calcium oxide, the amount of energy released is minus 3.591. So what if we add 1 mole of calcium oxide? So that would be equal to minus 3.591 divided by 0.0179. So 3.591 divided by 0.0179. So this is 200.61 minus 200.61 kilojoules per mole. So this is the amount of energy released when 1 mole of calcium oxide reacts with excess hydrochloric acid. Alright, now the next part of this question is use your values for delta H1 and delta H2 to calculate the enthalpy change for the decomposition of calcium hydroxide for this reaction. Right, we have to calculate the delta HR of this reaction from delta H1 and delta H2. Show clearly how you obtained your answer by drawing a Hess's law energy cycle, which says that energy change does not depend upon root. According to Hess's law, energy change does not depend on path or root. It only depends upon the starting point and the ending point. So we have to draw an energy cycle And if you are unable to calculate the enthalpy changes, assume that delta H1 is minus 129 kilojoules per mole and delta H2 is 150 kilojoules per mole, and these are not the correct values, right? So we are going to do this with our values, but first we have to draw the energy cycle, right? So we have to calculate the delta HR for this reaction, and what equations we have? We have delta H1. Let me write the equations here, which is calcium hydroxide reacts with hydrochloric acid to give calcium chloride plus water. This is delta H1. And if we balance this reaction, this is 2HCl and 2H2O. And the other reaction, delta H2, calcium oxide reacts with hydrochloric acid. We get calcium chloride plus water. Again, we get water. And this is 2HCl. Now the values which we get for delta H1 and delta H2 is, for delta H1 we have minus 102.67. So this is minus 102.67, and delta H2 is minus 200.61. Alright, so by using these two values, this is delta H1, this is delta H2. So by using these two values, we have to calculate the delta HR for this reaction, right? So if you look at this reaction, reaction number 1, where the calcium hydroxide is decomposing into calcium oxide and water. So we have calcium hydroxide on the reactant side and calcium oxide on the product side. So to draw the energy cycle, let's suppose if we react calcium hydroxide with hydrochloric acid. If we react calcium hydroxide with hydrochloric acid, so the products which we get is calcium chloride plus water, right? And the amount of energy change which occurs in this process. Now this is delta H1, and the amount of energy change which occurs in this process is minus 102.67. Now the other energy change which we have is when calcium oxide reacts with hydrochloric acid, again we get the same products. So that means we can draw another arrow from calcium oxide, that if we react calcium oxide with hydrochloric acid, again we get the same products, calcium chloride and water, and this time the energy change which occurs would be delta H2, and this is equals to minus 200.61. So we have drawn the energy cycle. This is now the energy cycle, and it says that if you just follow the arrows like from this side towards this side. So what it says that if we decompose calcium hydroxide into calcium oxide and then we react it with hydrochloric acid, we get calcium chloride and water. And if we react calcium hydroxide directly with hydrochloric acid, again we get hydrochloric acid. So either you do it in this single step, or you first convert it into calcium oxide and then convert it into calcium chloride. Either way you will get the same energy change. According to Hess's law, if this is delta H1 and this is delta HR and this is delta H2, so according to Hess's law, delta H1 would be equal to delta HR. We are adding these two sides, where the arrowhead of this reaction is combining with the tail. So we are adding these two sides and equating it with this delta H1. So delta H1 is equals to delta HR plus delta H2. Delta H1 is equals to delta HR plus delta H2. So delta H1, the value which we have for delta H1 is minus 102.67. is equals to delta HR, this we have to measure, plus delta H2 is minus 200.61. So let's find out the delta HR, which would be equal to, delta HR would be equal to minus 102.67, and this is minus, so when we shift it on the other side it becomes plus 200.61. So minus 102.67 200.61, we get 97 point plus 97.94 kilojoules per mole. Because this is an endothermic reaction, decomposition reactions are endothermic, so we get our answer in positive. So this would be the final answer, plus 97.94. And for this we have to draw this energy cycle, right? You have drawn this energy cycle and finally we get an answer. So when you draw the energy cycle, you can easily calculate the delta HR, right? By just following the arrows, we have made this equation that delta H1 is equals to delta HR plus delta H2. Delta H1 and delta H2 we already know, so that we can calculate the delta HR. Alright, now the next part of this question is, give a reason why FB2 was heated before FB3 or FB4 were added to it. Right, before adding FB3 or FB4, you have heated the hydrochloric acid. So the reason why we have heated the hydrochloric acid, it is very simple: to speed up the reaction, to increase the rate of reaction. Now the next part is the procedure in B was repeated using the same mass of calcium oxide FB4. However, 30 cm³ of 4 mole per dm³ HCl was used instead of 30 cm³ of 3 mole per dm³ HCl. Means we have taken the same volume of HCl, but instead of 3 mole per dm³, now we are using 4 mole per dm³. So how would the temperature rise compare with the one you obtained in the experiment in B? So with 30 cm³ of 3 mole per dm³, the temperature rise which we get was 28.5 degrees centigrade. With this we get a temperature rise of 28.5 degrees centigrade. So they are saying if we use 4 mole per dm³, what would be the temperature rise? Would it be higher than this value or lower than this value, or it would remain same? So it would remain same. We get the same temperature rise. And the reason is that we are using acid in excess amount. If you move to the first page of this question, they have clearly tell us that we are using excess acid. So the concentration of acid will not decide the extent of reaction, right? Because calcium oxide is the limiting factor, and once calcium oxide would finish, the reaction would automatically stops, right? So that means the temperature rise will not depend, although reaction may occur at a higher rate when you use 4 mole per dm³, the rate of reaction will increase, but they are not asking for the rate of reaction, they are only asking for the temperature rise. So it would be the same temperature rise because acid is in excess amount. As acid is in excess, so it will not decide the extent of reaction. Alright, so this is the end of this question, and hopefully you have understand everything which we have discussed in this question. Allah Hafiz.